The atom is one of the most basic concepts and most complicated concepts in chemistry. So today in this video, I wanted to give you some of the background on the people that helped develop atomic theory and what those ideas are. It's probably not as important their actual names, but understanding their names and their history will sometimes give you appreciation for all of the work that went into developing the atomic theory that we utilize today. The first theory is Dalton's atomic theory. So he has 4 principles. The first is elements are made up of tiny particles called atoms. The second is that each atoms of a given element are unique and different elements are different. So these two kind of work together because you've got little ideas, little bitty indivisible particles is what you're thinking about, and one atom of hydrogen is different than an atom of carbon. They look different whenever you look at them. It's sort of like how the 6-pronged Legos are different than the 4-pronged, and they each have a different purpose and they're both used for different things. Number 3, chemicals are combinations of atoms that combine in specific ways. It's that specific ways that really sets this theory apart. They don't just combine all willy-nilly. They will combine in a certain manner. And then last but not least, in a chemical reaction, the atoms are not changed, only reorganized. This relates back to that law of conservation of mass that we have discussed prior. You can't just come up with new atoms out of nowhere. They will be reorganized, reutilized in other forms and fashion, but they're not changed. They're still, a carbon atom is still a carbon atom. We can't just turn it into something else because we want to. I like to think about this like a ball pit. Whenever you jump into a ball pit, those different color blocks, they get reorganized in all these different ways, but in the end, you didn't change the number of balls in the ball pit. You just moved them around a little bit. And that's basically what the universe is doing. The universe is our giant, fun ball pit to play in. All right, so now let's talk about all the discoveries. So the first one is J.J. Thomson. And so what he did was he passed electricity through a glass tube, and then he did that both with and without gas in the tube. And he was able to tell that he would get different glowing. This is the same type of glowing that those old school monitors that you may or may not have seen. It's this cathode ray tube. It was what was in the back of this monitor, and it's what projected the light onto the screen. And so what happens is you actually have a stream of particles, and those are negative particles. So he kind of helped discover these electrons. And that stream of particles is what's going to release some of that light, and they'll only happen if you apply electricity to the alternate ends of this cathode ray. And they also found out that these rays were produced at the cathode, and so the cathode and it's going to be repelled. So that's how they realized that, oh, if the cathode is positive and the stream is going to be repelled by the cathode, then it must be negative. So he helped determine that electrons are negative. J.J. Thomson introduced the plum pudding model. This was one of the first models of an atom, and this is not the one that we have today. Plum pudding is what you see in the bottom left-hand corner, where it's more of like a cake with like raisins disseminated amongst it. So when you think about the plum pudding model, even though plum pudding is not something that I've ever eaten, just picture like a gooey ball with like raisins embedded within it. Sounds amazing, doesn't it? But he proposed this model, and it really kind of helped them figure out the different components and led to the models that we use more often today. So this has also led the discovery of the electron. They learned that since there is an electron, atoms are no longer just indivisible, because they thought an atom was just an entity, like you had a carbon atom. They didn't know that there were smaller particles within it. So that's why the atomic theory that Dalton proposed has been slowly changed with time, but the 4 tenets are still pretty strong, but it's just they're getting understood more strongly. These atoms are no longer indivisible because we now know about protons, neutrons, and electrons. The thing is, he knew that the electron was negative, but he also knew that atoms were known to be neutral. So how is it possible if we know electrons are negative? And so what he suggested was, oh, it must be this positive goo with electrons that are negative embedded within the goo. Because if you have a positive goo and negative particles all throughout, therefore it could very well be a neutral atom. And so he also utilized these cathode ray tubes prior to look at the deflection of these electrons. And by looking at the deflection, how much, if you apply a positive charge or to it, and then you look at how much that negative stream of electrons is deflecting, he was able to figure out how massive those particles are. And so he was able to figure out how big basically an electron is. And so this is the equation that he used to figure out that basically an electron weighs what you see here. You've got negative 1.76 times 10 to the 8th coulombs per gram. So that's the charge per the mass of that particle. Then along came Millikan, because we really wanted to figure out the exact mass, not just a ratio of that mass of the electron. So Robert Millikan proposed the oil drop experiment. What he does is look at number one. Number one is where you take a mist of oil droplets and they're getting injected into a chamber. And then gravity acts on it, so these oil droplets start to fall. But at the same time, they're going to fall and pass through a very small pinhole, and that pinhole is going to be in a positively charged plate. Then you have a negatively charged plate on the bottom. And so what's going to happen is these oil droplets are going to stop somewhere between the positive and negative charge. And that is going to be where the negative force that is going to be repelling that particle and the force of gravity is going downward. It was able to use those opposing and opposite forces to figure out more information about that electron. And in this case, we're figuring out what is the mass. That's sort of like how balances work today. We know how much gravity is on Earth, and so we know that based on the force, downward force, and how much gravity is, we can tell the difference whenever you're stepping on the scale versus not. And so we're able to tell a mass from a differential. It's just they used electricity to help figure this out. So kind of from all of this research we talked about, we know that the particle is found in cathode rays. That was our electrons. It is the fundamental unit of all atoms. It is negative. We know its mass, and we know it's charged. And so all of these are just very important chemical and physical properties. But basically, the electron exists. Yay! And we know a little bit about it. And so that is a very important thing. For you, what you need to know is that mass is extremely small, and it is negative. If you can understand those two principles when we keep going, this will help you a lot. Next up was Henry Becquerel. Basically what he did was, it was an accident. It was an accident in the lab. He accidentally walked away. He put some rocks down on his photographic plates. A lot of chemists were also into photography, as were a lot of biologists. And he accidentally, when he left them on the plates, he came back and he discovered that portions of the plates had been exposed to something that caused the plates to become developed. And so what he noticed is it was the shape of the rocks. And so what he was noticing, these rocks were actually emitting some kind of energy that was causing these photographic images to become developed. And so with that, he discovered radioactivity. He went on to discover that there were alpha, beta, and gamma particles. An alpha particle is just a helium nucleus, a beta particle is an electron, and gamma particles are light. And so alpha is the least dangerous form of radioactivity, with gamma being the most dangerous, where you do not want to get exposed to gamma light. Next up is probably my favorite experiment. It's Rutherford's gold foil experiment. It's a really neat experiment. So what he said was, okay, we've got this plum pudding model. And the idea is, if we have this plum pudding model and electrons are so stinking small, if I take this helium source, or this lead source, and I shoot alpha particles at it. Alpha particles are pretty big, okay? They're a helium nucleus. So they're the second smallest element, but they're huge compared to electrons, okay? So what he thought was, if the plum pudding model is true, then when I shoot these alpha particles at a piece of gold foil that's really, really thin, they should just pass right through. Because it's sort of like if I were to take a pistol and shoot a bullet at a piece of paper. Nobody would expect anything else but for that bullet to pass through the piece of paper. But what happened was these alpha particles were bouncing off and deflecting in all of these crazy directions. And he went, what in the world is happening? And then, like any good chemist, he took notes, he made observations, and then he figured out what was really happening. And in this case, he proposed a model for a nucleus that was much better than the plum pudding model. This basically is the nuclear theory of an atom, which is what we believe and what we are basing a lot of our theories off of today, is the idea that there must be some dense portion of the atom, because electrons, remember, are so small, so they can't be accounting for the deflection. So there must be some dense region of an atom that would cause this giant alpha particles to get shot in all directions. We need like a piece of lead in front of the bullet, not just a piece of paper. And that's essentially what the nuclear theory does. It says if you have a really strong, dense nucleus, then you can have deflection of some of the alpha rays. Not all, because notice how most of them are going to pass through the open space that is the rest of the region of the atom. But that nucleus, it is dense. It is so dense that those alpha particles could just bounce back off. All right, but then there's the question of, could the nucleus be composed entirely of protons? If we look back here at this model again, your nucleus is in the middle. If it were entirely made up of protons, if you put two positive things next to each other, what happens? They repel, and they repel strongly. So he said, so we went forward to James Chadwick, and he proposed that there has to be something that is holding these positively charges together. And so with that, he proposed a neutron. And so how he did that was he looked at different radiation signatures, and it was not something that could have been produced by either an electron or a proton. And so he said there must be some other fundamental particle of an atom, and with that he proposed a proton, and now we know there's protons, neutrons, and electrons, and voila, the nuclear theory is really coming to play. Now these are the main take-home pieces of the nuclear theory of an atom. Most of an atom's mass and all of its positive charge is in the core of a nucleus. Remember how I said electrons were so stinking tiny? They are so tiny. They make up this 0.01% of an atom's mass, so they're negligible. Most of the mass is going to be due to its positive charge and its neutral charge, the protons and the neutrons. You also need to remember the neutrons are neutral, protons are positive, electrons are negative. Next, most of the atom's volume is empty space. Look at this nuclear theory. See how most of it, that yellow part, we're going to assume that's mainly neutral. I mean, it's going to be mainly empty space through which the electron is going to follow. Okay, but the electrons are within that yellow portion, and so those are negatively charged, but they're dispersed all throughout that empty space. So if I were to ask what makes up most of an atom's volume, it's empty space. What makes up most of an atom's mass? That's the nucleus. Some other premise tenets that's really important is that negatively charged electrons must be equal to the number of positively charged protons if your atom is neutral. And that makes sense. If you've got a charge of 0, plus 1, minus 1, that equals 0 together. All right, so then here's kind of a charge table summarizing this. Is that electrons are really stinking small. Look at that exponent, 10 to the negative 31. And then the exponent on the protons and the neutrons is about 10 to the 27, negative 27. So that's 4 orders of magnitude different. So we're talking about 10,000 times heavier is what the proton and the neutrons are compared to the electron. And then the charge is extremely important. This is an interesting note, which we'll get into much longer whenever we talk about radioactivity, and that is that neutrons can actually decay into a proton and an electron during beta decay. And so if you add together the mass of a proton and electron, you get basically a neutron, which makes sense because neutrons are neutral and they could be composed of an electron and a proton. So that's really kind of fun to remember. And if you ever ask which one's heavier, a proton or a neutron, it's a neutron because it could decay into both a proton and an electron. All right, so stop the video and try and answer these questions, because if you can answer these questions, you've understood the bulk of what I'm trying to get across in this video. And that question is, what subatomic particles are in an atom? What makes up most of the mass of an atom? And what makes up most of the volume of an atom? So the answer to the first question is, what subatomic particles are there? Protons, neutrons, and electrons. What makes up most of the mass? That is the nucleus, and the nucleus is composed of the neutrons and the protons. What makes up most of the volume of an atom? And I would say to that, it's the electrons, which roam around in empty space. All right, our next video is going to be talking about how do we use elements and symbols and subatomic, like mass numbers and atomic numbers, in order to describe elements. And that's what you see here. Our mass number, that just tells you how heavy does the subatomic particle or our atom weigh. And your mass number is going to be a combination of your protons plus your neutrons. And that's because, remember, your electrons are so insignificant, they weigh so little, we don't care about them. So what is the mass of the particle mainly based on? The protons and the neutrons. And then your atomic number is just how many protons. The most important thing here is if you change the number of protons, you're changing the element. No elements have the same number of protons. So if I tell you my atomic number is going to be 6, there is only one element that can fit that bill. And which one is it, you may ask? If we come over here, you'll look and you'll see carbon, and carbon is right here. Carbon with 6 is a number. See this little 6 up here? That tells you that it has 6 protons, and that is its atomic number. All right, so there's the symbol, there's the atomic number, and there's the mass number. X just stands for any element that you want. A is the symbol for mass number, and then Z is our atomic number. You'll also see it on the periodic table like this, where your atomic number is above the element symbol, the average atomic mass is below it. For the sake of these next couple of types of questions, we're going to assume it's atomic average mass. We're just going to round it, and we're going to pretend that 9.01 is around 9. We'll figure out more about where that comes from when we talk about isotopes. And with that, that's the important part. Go watch the next video to help you practice a little bit more about figuring out what are all the subatomic particles of every element on the periodic table.